Yeah, so in terms of circuit classes and results about them. Okay, so just a very brief intro to circuit complexity. So what are we interested in circuit complexity? We're interested in mainly the question of low bounds. Given a circuit model C, can we show there's an explicit Boolean function that does not have small circuits from the class C? And typically, by explicit, we mean a function in NP, because the main goal of this area is to make progress towards separating NP from P. But we could have other notions of explicitness too. I mean, quite often we get functions in P where we get hardness results. And if we can't prove hardness results in NP, we're willing to settle for hardness results in exponential time even, which is relevant to de-randomization results, or even in non-terms of exponential time. And even here, you typically want super polynomial size low bounds, but anything superlinear is interesting when the circuit class is strong. So the default choice of the class C here is general Boolean circuits. But there are various ways of restricting the class of circuits we consider, because it seems like a very hard problem to prove low bounds for general Boolean circuits. And this is something that we'll go into a bit further later. So we're going to relax this objective of proving low bounds for NP against Boolean circuits in two ways. One is to consider a restricted class of circuit C. So for example, where the depth of the circuit or the set of gates that are used in the circuit are constrained in various ways. So that makes a low bound task simpler because C is restricted. But the other way in which a low bound task can be simpler is if our low bound is less explicit. So instead of looking for a low bound in NP, if we are happy with low bound in, say, exponential time or in some even larger class. Okay. Why do we care? Well, yeah, so from the point of view of proving low bounds for separating NP from P, you care because you want your upper bound to be in NP. But you also care from the point of view of de-randomization, because in the complexity theoretic setting, so de-randomizing BPP, putting it in P on sub-exponential time corresponds to circuit low bounds and exponential time. So there, circuit low bounds where the explicitness of exponential time are already useful. So these are two different reasons, but there are others. Yeah. Okay, so which circuit classes do we typically consider? I mean, there are, of course, many circuit classes that are of interest, but these are the main ones in terms of making progress in circuit low bounds. So AC0, which is just constant depth circuits with unbounded fan-in and/or NOT gates. So if you have a constant depth circuit, namely a circuit where every path from an input to the output gate has constant length, then you need to allow the fan-in to be unbounded. Otherwise, the output gate will only depend on a constant number of inputs. And so that makes the class trivial in terms of computing Boolean functions. If you're computing multi-output functions, it's still interesting. There's interesting cryptography that can be done in that space. But if you're considering Boolean functions, then this is what makes it interesting, when you have unbounded fan-in. And so this is somehow the simplest class that where kind of, it becomes non-trivial to prove low bounds. And then we can sort of enrich this class a bit. You can kind of add more gates to it, mod P gates. So these are gates where the gate outputs 1 if the number of inputs is 0 modulo P, if and only if the number of inputs is 0 modulo P. And it turns out to make quite a difference for proving low bounds whether P is prime or composite. So the case where you have M where M is composite, that's ACC0, which is potentially a larger class in AC0 mod P. And then you have TC0, which is still we're living in this space of constant depth circuits with various kinds of gates. Here you have unbounded fan-in threshold gates. So each gate says, well, some linear kind of function is at most some number, right? Sigma AI xi is less than or equal to b, where ai's and b are some integers. So that's what a threshold gate is. And TC0 is a set of constant depth, is a class of constant depth circuits, so unbounded fan-in threshold gates. And then we have formulas. These are just circuits which are trees, where the graph of the circuit is a tree. So each gate has fan-out 1. And this is essentially equivalent in terms of size in the polynomial size regime to log depth circuits. And then we have general Boolean circuits, which we know very little about. Okay, so these are circuit classes we're interested in, and what kinds of low bounds do we know? So first of all, there's a hierarchy. It's a natural hierarchy of circuit classes. So AC0 is contained in AC0 mod P. It's contained in ACC0. I guess these two inclusions are not completely trivial, but they're not too hard to see. If you have ACC0, you can simulate it with threshold gates, and similarly, each threshold gate can be simulated by a polynomial size formula. So the other inclusions are all trivial. So this is a hierarchy of circuit classes, and we'd like to get low bounds for as large a class here as possible. So what's the state of the art? So this kind of enterprise goes back to the 80s when there was a strong sort of drive to prove, to try to solve NP versus P by proving low bounds against stronger and stronger circuit classes, progressively stronger circuit classes. And this started off with these breakthrough results on AC0 by Aitai, First Saxipsa, Yao, and Haustad. And now we understand the constant depth circuit complexity of parity very, very well. And what they showed is that the parity function is not an AC0. So if you want to compute the parity of n input bits, that's not an AC0. And quite shortly afterward, Rasbrow and Smolensky sort of extended this to circuits which have mod P gates, and they showed for each prime P that the majority function is not an AC0 mod P. So, I mean, these results are nice, and they use very interesting techniques. So here, there's a sort of random restriction technique, which is developed for this purpose and has been useful in various other contexts. And Rasbrow and Smolensky used the polynomial approximation technique, which again has been extremely useful. So technically, these results are very useful, but in terms of what they're saying, it's not very satisfactory in the enterprise of proving low bounds, because parity and majority are essentially trivial functions, right? They're functions that are very easy to solve. And this is really not, so you don't really expect these techniques to work in terms of separating NP from P. So there was quite a gap after this in terms of proving low bounds for circuit classes. So it's only sort of very recently that something non-trivial was done for ACC0. So Ryan Williams showed a low bound in non-termsheet exponential time against ACC0, and recently he and Cody Murray sort of brought this down to non-termsheet quasi-polynomial time. So they showed that non-termsheet quasi-polynomial time doesn't have ACC0 circuits. So already adding mod M gates seems to make this task of proving low bounds much, much harder. And we don't completely understand why this is the case. Perhaps in David's talk, we'll kind of get some sense of it. So this is kind of interesting. But notice that there's a sort of a difference between this and the previous results. So these results are both for problems in P. So you have a problem in polynomial time for which you're proving a super polynomial low bound. Here, the low bound is super polynomial, but the upper bound here, the non-termsheet time required, is quasi-polynomial. So this is sort of like the cryptographic regime where the upper bound is using more resources than the low bound. So that's qualitatively a different kind of result than the results here. And really, if you're trying to prove NP versus P, we want to be showing a low bound in NP against ACC0, and we have no idea how to do that.
How explicit is this?
So the way it works using indirect diagonalization. So what you get is essentially that some hard problem in an NQP or NX, which can be shown to be hard using the time hierarchy theorem, is not in ACC0. But then that implies, using the completeness with respect to these classes, that the complete problems are not in ACC0.
So,
yeah.
Okay, so the complete problems, pick one of them, it's not.
Yes, yeah.
You have complete problems, so this quasi.
Yeah, maybe not so natural ones. I mean, just the canonical complete problem, which is run the machine for quasi-polynomial time. Yeah. So no, even Ryan's original paper, the technique isn't obviously natural, but there's some, well, it's not always clear what it means for a technique to be natural. Does it naturalize is a question. Nobody has found a way to naturalize it. And because it uses diagonalization. Yes, yeah. No, not for ACC0. For AC0 mod P, yeah, which is different. Yeah, for AC0, we don't know how to naturalize it. Okay, and basically in terms of super polynomial low bounds, we're stuck here. We don't know anything for TC0, even for depth 2. So one barrier is showing a low bound NP against ACC0. Another is showing low bound NP even against depth 2 TC0 circuits, circuits with 2 layers of threshold gates. And in terms of formulas and circuits, well, there's some results which are sort of like morally weaker. So based on work of Andreev and Haustad, we know there's a function in P which doesn't have subcubic size formulas. That's the best known formula size low bound. And for circuits, I have a result which says that the class Merlin-Arthur polynomial time with 1 bit of advice. So let's just ignore that 1 bit of advice for now, which is essentially a probabilistic version of NP is not in circuit size n to the k for any fixed k. So for any fixed k, there's a language in MA with a little bit of non-uniformity, which does not have circuits of size n to the k. But again, this result is like this, where the upper bound has more resources than the low bound. So it's more in this sort of like complexity theoretic setting rather than this cryptographic setting.
And the formula thing, the function itself has a small circuit. Like how small the circuit is? I mean, it's polynomial.
It's pretty tight, I think. Yeah. I mean, I think it has cubic size formulas are close enough. Yes. Yeah. So yeah. I mean, there is sort of like a candidate approach using KRW, so-called KRW conjecture to proving low bounds here, but progress is quite limited so far. Yeah. Okay. So that's the state of the art of low bounds. So just to kind of encapsulate it. Here's what we have. So here's where explicit low bounds are known for these two classes. But these results all go back to the 80s. And here we are 30 years later. And OK, we have a new low bound for NQP, which is very interesting. And it's ACC0, but very little known about these other classes. So yeah, I just wanted to give you a brief tour of circuit complexity because it's a circuit complexity session. But let's get on to the connections to the cryptography now. OK, so yeah, when I was a graduate student, I sort of like was just reading papers quite broadly, and I read some crypto papers and found them quite interesting because it seemed to me that it had the same flavor as complexity. They're essentially doing complexity in some form, using circuits. Everything's formulated in the language of circuits. And I mentioned this to my advisor, Lance Fortnow, and he was just completely taken aback. He couldn't understand how I could make such a mistake, and complexity and crypto are clearly so different. And this is something that I've sort of maybe tried to kind of like understand later. Well, what is it that makes cryptography different from circuit complexity? And I guess they're trying to study the same phenomena, but there's just a very big difference in emphasis. In circuit complexity, what we're typically interested in doing is showing provable hardness. For a given circuit class C, can we show the explicit function is not in C? And in cryptography, we're interested in provable consequences of hardness. So there, it makes sense to take a certain hardness assumption that's plausible or at least not yet broken and ask how much cryptographic leverage can we get from A. So there's a sort of cost-benefit analysis where you're kind of paying for this hardness assumption, but then how much can you get out of it? And here we're very much interested in what can you prove to be hard. And there's a big gap between these because we understand so little about computation. So we are sort of interested in very different parts of the space, but yeah, the phenomenon we're studying is probably quite related. So yeah, so that's my kind of perspective on the differences between the areas. But there's also sort of clear connections because, as I'll go on to describe in more detail soon, crypto has been applied to understand the hardness of proving low bounds in circuit complexity. The natural proofs barrier, Rouse-Brown-Rudich, depends very much on cryptographic hardness assumptions. So the cryptographic hardness assumptions help explain the difficulty of proving stronger circuit low bounds. And also, well, I mean, clearly, lots of interesting problems in cryptography are defined using circuits. Canonical problems for various, for crypto, such as complete problems for SZK and other problems involve circuits. And in particular, in this talk, I'm going to talk about the minimum circuit size problem and its relevance to crypto, and that's a problem, clearly, that's about circuits. OK, so we've seen this in a couple of earlier talks, but let me just quickly go over it again. So there's this paper of Russell and Pagliazzos from the 90s where he discusses these sort of 5 worlds of cryptography, which is probably somewhat outdated because there are all kinds of new primitives, and so there are many, many other worlds out here, but we don't even understand the relationships between these worlds very well. So yeah, so essentially think of this as going in kind of like direction of increasing hardness. So we're getting more and more hardness as we go to the right. So here you have that NP is easy in the worst case. And what Impalazo does, and we'll do too, is sort of leave it unspecified what easy means. It could be polynomial time, probabilistic polynomial time, polynomial size circuits. That's fairly flexible. But yeah, let's just leave that open for now. So Algorithmica is this world in which things are easy, right? And which it's good for us because we can solve NP problems easily. Yeah, there's perhaps even easier worlds where you can solve polynomial space problems easily and so on. But yeah, but that's what Algorithmica is. Then there's Heuristica, where NP is sort of average case easy, but worst case hard. And for most concrete kind of algorithmic applications, it's probably good enough that for any sort of reasonable distribution of instances, you can still solve it efficiently. Then there's this kind of very frustrating world, the worst of all possible worlds, Pessilent, which is where NP is average case hard. So it's hard on sampleable distributions, but you can't construct one-way functions. And one-way functions don't exist. And then there's minicrypt, where symmetric key encryption exists, but public key encryption doesn't. And then finally, Cryptomania, where public key encryption exists, right? And well, the question is, well, do we really need all these worlds? Which world do we live in? How much evidence can we get that we're living in one of these 5 worlds, right? So what we'd really like to do is kind of like annihilate a few worlds, right? So kind of get rid of a few of the worlds. Try to kind of zone in on the true world that we live in. Now, somewhat surprisingly or strangely, I mean, I think current proof techniques can't really distinguish between the farthest of these worlds. So this world and this world are pretty much indistinguishable in terms of the proof techniques that we have. We can't really distinguish between things being very easy and things being very hard. But what we can hope to do is to perhaps rule out some of these intermediate worlds, say that maybe heuristica or Pessilend just don't exist. So that's the question that I'm kind of interested in here. So this is, of course, something that's been studied before, and there's various results about it. For each of the worlds in Impala's original paper, he gives an oracle or mentions oracles relative to which each of those worlds exists. And then there's other kinds of results. So Andre and Luca show that if there's worst case to average case reduction for NP that's non-adaptive, then the polynomial hierarchy collapses. Co-NP is an AM/poly. And similar results were shown by Akavia et al. And Andre and Chris for various kinds of black box reduction from worst case hardness to existence of one-way functions. So we have sort of negative results in black box settings and relativized settings. In terms of positive results, we don't have too much, but I mean, there is this paper of Andre with Kunal Talwar and Andrew Wen, which shows that if NP is not in BPP, then there exists a very weak form of one-way functions where, well, I mean, the function requires more time than is allowed to the adversary, but at least you can verify the function value quickly. So it's perhaps not very useful for real-world cryptography, but it still seems somewhat non-trivial. And this builds on work by Godefroy, Chartel, and Tashma, who show that if NP is not in BPP, then you can actually generate hard instances given any candidate algorithm. So if NP isn't in BPP, then you give me any sort of probabilistic machine, and I can use the probabilistic machine to generate hard instances for that machine. So this works in sort of a non-black box way. It doesn't use, so it actually uses the code of the machine. And perhaps techniques of that sort could help us understand these connections better.
So the time it takes to generate a hard instance is more than the time.
Yes, absolutely. Yeah.
Black box, just the size of the thing is enough, right? You don't really need the code. The size of the code.
Yeah, but the follow-up work by Serias, where right in like,
So you need the size.
I think it can be interpreted the same, the size.
Yeah. So.
And also you need to have an oracle to compute with it, right?
So the oracle and the size might be enough. Okay, so far, like what I've talked about in terms of separating these worlds is in Impala's original formulation, where you consider hardness of NP and hard and average and so on. So implicitly, you're thinking about satisfiability, which is a canonical NP complete problem. And it seems difficult in general to do hardness amplification for SAT, as we saw with some of the black box results, or to use average case hardness of SAT to get one-way functions. So, well, the general sort of message in this talk is that perhaps these problems become more tractable, or there are more approaches to them, if instead of SAT, we consider the minimum circuit size problem, which is a problem that in the past few years, the past 2 or 3 years, has seen quite a lot of work, and which I think might be better suited to kind of working with these kind of cryptographic settings than SAT is. But yeah, before talking about that, let me just say, first of all, what MCSP is, because it's possible that many of you don't know of it. It's something that mostly complexity theorists talk about. So what is this minimum circuit size problem? I mean, it's a very natural problem. You're given as input the truth table of a Boolean function f on n bits, little n bits. So we'll always have through this talk these two parameters, little n and capital N. Little n is the input size for this function f, and capital N is the size of the truth table, which is 2 to little n. And you're given a parameter s. And the output is yes, if and only if f has circuits of size at most s, right? So it's a very natural problem. Can you compress the string when you interpret the string as a truth table by using Boolean circuits for the function represented by the string? That's essentially what's being asked here. So note that MCSP is an NP because you can just guess a circuit of size at most s, and you're given the entire truth table, so you can actually verify that the circuit computes each input in the truth table correctly. So that's a polynomial time check. So there's actually several variants of MCSP that you could define and that make sense and are interesting. You could, given a fixed s, a function s from the natural numbers to natural numbers, you could fix the size parameter to s as a function of n. And that's the variant that we're considering through most of this talk, because for the results that I mentioned, it seems the most reasonable one. It's more natural to put a distribution on this. There's also average MCSP, where you can ask if F is computed by circuits on most inputs rather than on all inputs. And you could also ask, you could parameterize the problem via a class of circuits C, right? So given a class of circuits C, you could ask, well, here does F have size S circuits from the class C? So I mentioned all these classes of circuits earlier, and for each of them, you could ask the MCSP question. And somehow this MCSP problem is a problem that captures all low bounds, right? Because every no instance of MCSP is a low bound, and I mean, low bounds are precisely no instance of MCSP. So there's one computational problem that somehow captures low bounds questions. And so it makes sense that it'd be interesting to understand its complexity and to try to show things about it. And this turns out to be quite a difficult task, but yeah, but there are some interesting aspects to it.
How does it relate to hardness of learning? Assuming that you have all the samples, it seems like this is kind of
yeah, exactly.
CMSCSP is kind of proper learning.
It's very closely related to the hardness of learning. Yeah, that's exactly right, because learning is sort of closely related to the search version of MCSP, right? Because you're given the truth table and you want to find a small description. But you're given the entire truth table. So learning is like the implicit version of this, where you're given Oracle access to the truth table and want to find some approximate circuit. But yeah, there's various connections between the search version of MCSP and learning. Yeah, in the search version, well, you could ask to produce C circuits, or you could just ask to produce any. So both proper and improper learning could be fitted into this framework.
So here the parameter S of interest is S usually polynomial in little n, or S of interest would be even like 2 to the n or 2 or something?
Yes, so those are two main regimes of interest that I'll be referring to. So one is where S is polynomial in little n, and the other is 2 to the epsilon n for some epsilon. Yeah.
Is there a reduction of search to decision?
So there's not quite a reduction of search to decision, but there's an approximate search to decision reduction. That follows from this work, which I'll be mentioning soon, of Kamosino, Palazzo, Cabinets, and Kolokolova, which says that even if MCSP is easy on average, you can solve the search problem approximately. So it's kind of like even under a weaker hypothesis, you get a search problem, a solution to a search problem, but it's only approximate. It's not an exact solution.
So if the search problem is hard, the decision problem is hard on average?
Yes, yeah.
Like a boosting-based proof, or how does it?
So that proof goes via pseudorandom generators, so-called learnable pseudorandom generaters, where you base a pseudorandom generator on some function f, and if f is hard, you get a generator, and if it can be broken, then you get circuits for f. You're able to learn f, and that can be used to solve the search problem, essentially. Yeah. Okay. So this is sort of like a kind of an evangelical slide. I mean, MCSP is arguably as fundamental a problem as SAT, but well, it's sort of a dual problem to SAT. In SAT, you're given a circuit and asked what it does, and MCSP, you're given a truth table and asked whether it corresponds to small circuits. But it's been studied and is understood much less. So historically, it goes back even earlier than SAT to the 50s to work in the former Soviet Union, but I guess there's just much less that's known about it, and so there's been much less progress on it. And the long-standing open problem about MCSP is MCSP NP complete, right? So it's an NP problem. Like SAT, it feels like a pretty unstructured problem, but we don't know how to show NP completeness for it. And this has been a question that's been open for a very long time, and in fact, the stories that Levin delayed publishing his proof of the NP completeness of SAT because he also hoped to show the same result for MCSP, but he finally wisely chose to publish because it's still open. There's MCSP for other circuit classes, for weaker circuit classes, is also interesting. And it's been known for a very long time that DNF MCSP is NP complete via reduction from set cover. Well, I think Masek's original reduction is from circuit set, but it's easier to do it from set cover. So when C is a simple class of circuits, somehow NP completeness is easier to show, which is a bit counterintuitive because you'd expect that solving the problem should get harder as C gets to be a richer class of circuits. NP completeness is unknown even for the variant of the problem where C is depth 3 circuits. So even this is unknown. And it's perhaps an interesting problem if you want to get into MCSP. There's some understanding of why NP hardness is difficult to show. And the reason is that it is strongly connected to low bounds, right? So the idea is that if you showed the NP hardness of MCSP via a standard reduction, right? Just take a standard reduction which just works from an easy language, a language where yes and no instances are both easy to generate. Then if you just run the reduction on no instances, you're going to get a no instance of MCSP from it. And that means that you'll easily be able to generate no instances of MCSP, right? So you generate no instances of some easy language, run the reduction, you get no instance of MCSP, but that means you get hard functions. So that's something we don't know how to do, right? We don't know how to get circuit low bounds and exp. And so that seems to be a very hard question. So that perhaps explains at least why deterministic reductions of the standard form, the conventional form, are hard to show. But it
doesn't rule out Turing reduction.
Yeah. It doesn't rule out Turing reductions. It doesn't rule out randomized reductions, which would already be very interesting. So yeah, so it's not a complete explanation, but at least it ties the problem to the problem of showing low bounds. Okay. Okay. So yeah, I guess this is the question that was sort of that I'm interested in this talk. So can crypto be based on the hardness of MCSP, right? So well, I guess there's two natural questions corresponding to heuristica and pessilent. So like ruling out heuristica for MCSP and ruling out pessilent for MCSP. So the first question is, well, does worst case hardness of MCSP imply average case hardness of MCSP, right? We don't know how to say this for SAT. Can we at least say it for MCSP? And question two is, does the average case hardness of MCSP imply the existence of one-way functions? Well, so these sound like interesting questions, but we haven't even defined what it means for MCSP to be hard on average. So let's do that first. So try to find some reasonable notion of what it means for MCSP to be hard on average. We could just say, well, it's hard with respect to some sampleable distribution, but we want to choose some natural distribution, which makes sense here, and argue for hardness with respect to that distribution. And it turns out that this is very closely related to actually the original reason why MCSP was of interest in the complexity community, which is the natural proofs of Rasbrow and Rudich. So I'm going to tell you about natural proofs and then relate that to the average case complexity of MCSP. Okay, so Rasbrow and Rudich were motivated by the difficulty of proving low bounds, right? So you have low bounds for AC0, low bounds for AC0 mod P, but it seems hard to get low bounds beyond that. And is there a good explanation of this? That's what Rasbrow and Rudich were addressing. And what they wanted to identify was some sort of common feature of the proofs that worked to prove low bounds against AC0 and AC0 mod P, but were unlikely to work in stronger settings against general Boolean circuits. And they did this via this notion of natural proofs. So let's say you're given some complexity class D and a circuit class C. The circuit class C is a class C against which you want to prove low bounds. Think of this D as somehow the complexity of your proof, right? So you're trying to prove low bounds against C, but the complexity of your proof is somehow in this class D. So a D natural proof is a property of Boolean functions. These are functions that you're going to prove to be hard against C, such that you have these three conditions. The first is constructivity. This property needs to be decidable in D. I mean, that means that somehow that you're proving that these problems in Q are hard within D. Usefulness, which means that all the strings satisfying Q, all the functions satisfying Q are hard, right? So if a function satisfies this property Q, then it's not in C, then it's hard. And finally, density, so that at least that a significant fraction, a noticeable fraction of Boolean functions actually satisfy Q. That a random function satisfies Q with noticeable probability, right? So these are the three conditions for natural proof. So essentially, you're formalizing that for a random function, you can kind of efficiently, in this class D, prove low bounds against C. And it turns out that the known low bound techniques were all sort of formalizable in this way, right? So maybe a picture will help a bit. I mean, it's just a very schematic picture. So here are all the Boolean functions. Here are the hard functions. These are the functions, the easy ones, the ones in the circuit class C. And this is the D natural property. So think of D as being P or P slash poly, right? Or size of poly-size circuits. That's what we're going to have for the remainder of the talk. And Q is a property that can be checked efficiently and is fairly large. It occupies a significant fraction of the space of Boolean functions. Okay? Is that clear? So, I mean, essentially, what you do when you want to prove a low bound is sort of identify a natural property Q and then show that some specific function Q has that property. So, for example, if you want to prove low bounds for AC0, you identify a certain natural property and then show that parity has that property. And with AC0 mod P, you identify a certain natural property and show that majority has that property. Okay, so this is a framework, but then what can you say about it? So, well, first of all, Rasbrow and Rudich observed that the standard circuit low bounds, the low bounds would work via very concrete sort of algebraic or combinatorial arguments all yielded P natural proofs against classes C, where C is AC0, AC0 mod P. There's various other examples of weak classes against which you get low bounds this way. But the main theorem is that you couldn't really hope to do this for general Boolean circuits. If exponentially hard one-way functions exist under this cryptographic assumption, there are no P natural proofs against polynomial size circuits, right? And in fact, assuming kind of appropriate hardness assumptions, you can get this to work even against classes C that are only slightly above the classes where we know how to prove low bounds. For example, TC0 depth 4 and so on, right? And perhaps, David will have something more to say about this in the next talk. So this is the main theorem of Rasprov-Rudich. So let me just try to give you like a proof by picture of it. It's not hard to prove, but it's just conceptually very interesting because it ties together a lot of interesting directions: proof complexity, circuit low bounds, and cryptography. So here's sort of the proof of the main theorem. So we just need the GGM construction of pseudorandom functions. So if exponentially hard one-way functions exist, then there's some pseudorandom function family with polynomial size circuits which is secure even against exponential size adversaries, against size 2 to the order n, right? So let's assume that natural proofs existed. So here's a natural proof, which is decidable in polynomial time or in polynomial size. And here's your pseudorandom function family, which all lives within the easy functions, within polynomial size functions. It's supposed to be a pseudorandom function family, but here's this easy set, which is dense. It occupies a large portion of space, so it's a distinguisher. It's distinguishing random strings from pseudorandom strings. No pseudorandom string satisfies it, but a random string satisfies it with significant probability, right? So if a natural proof existed, it would break the pseudorandom function generator, and therefore you wouldn't have the security of the exponentially hard one-way function that you assumed, right? So that's just kind of a very quick proof by picture. So that's the sort of the main technical part of Rasprov-Rudich. Yeah.
It's insensitive to the size of the key of the PRF, right? You don't need like exponential hardness in the length of the key.
No, yeah.
All you want is to be like poly in size.
Yes, that's a very good point because later on I'll be focusing on the size of the strings in the range, the circuit complexity of strings in the range, because you don't care about the seed length or the complexity of the seed. Okay, so that's the Rasprov-Rudich proof. But what does this have to do with MCSP? If you just look at this, this property, so this is MCSP essentially, right? You're given Boolean functions by their truth tables. So this set here is essentially MCSP. And we'll think of existence of a natural property as some sort of zero-error average case easiness for MCSP, right? And I'll kind of justify that soon under the uniform distribution. So if you pick MCSP with some fixed size parameter, then the uniform distribution is a natural distribution to put on the instances, on the truth tables. But if you put the uniform distribution on truth tables, then it doesn't really make sense to consider bounded error algorithms because the algorithm that always says no is a very good algorithm. But it makes sense to consider zero-error algorithms, and that's what we'll do. So given a size function S, we say that MCSP of S is zero-error easy on average over the uniform distribution. And throughout, it'll be implicit that I'm working on the uniform distribution. If there's a sequence of polynomial size circuits such that on any input F with truth table of length n, Cn always outputs 0, 1, or question mark. And it never outputs the wrong answer. That's the zero-error part. And the average case success part is that it outputs a non-question mark probability with some significant, non-question mark value with some significant probability, 1 over poly of n, right? So that's our definition of MCSP as being zero error on average. And here's a simple proposition, which I'll soon again show you by proof by picture, that MCSP is zero error easy on average if and only if there are natural proofs. So this is completely equivalent to the existence of natural proofs. It's a natural notion of zero error easiness on average, which is completely equivalent to natural proofs. And why is that? Well, suppose you have a natural proof. So you have a set like this, which is in polynomials, which is decidable in polynomial size and occupies a large portion of the space. You just answer 1 or anything on the set, right? And question mark everywhere else. And that's a zero-error algorithm for MCSP, right? So that's a zero algorithm that works with noticeable probability. And the other way around, suppose you had an algorithm that was easy on average. The point is that you can just ignore the zeros, right? You can just kind of throw them away. Because the set of yes strings is sparse, so it doesn't really affect the success probability very much. So you just take the 1 strings, and the natural property corresponds to everywhere that the algorithm says 1, and that's natural property, right? So you just throw away the 0 strings, and yeah, and you get a natural property from it. The natural proof is essentially the set of 1 answers of this average case algorithm. Okay, so now, well, we have some notion of average case hardness or easiness, and we can ask about first these 2 questions that we had with regard to these notions. First of all, does worst case hardness imply average case hardness? And secondly, the question about crypto, right? So for the first question, so I'm not going to talk about this very much, but it's a very interesting paper by Shuichi Hirahara last year, which shows using sort of a non-black box argument, which is very closely related to the question you asked, Benny, and the answer I gave, which is that if MCSP is 0 error easy on average, then there is some epsilon such that the minimum circuit size can be approximated to within a factor n to the 1 minus epsilon, which is already non-trivial, right? So you give me a kind of a truth table of Boolean function, and I can output a number which is within the n to the 1 minus epsilon factor of the correct circuit complexity of that function. So it's not quite a worst case to average case reduction, but it's an approximation to average case reduction. And this just builds in a fairly straightforward way on this work of Carmesino and Palazzo, Cabinets, and Kolokrolova, which says that natural proofs implies learning, right? Once you have learning, then, well, you take a Serum generator that's based on a function f. If f is hard, then you use the natural proof and you get a hypothesis. It's not going to work. And if f is easy, the hypothesis is going to work, and you'll be able to check this by testing the hypothesis against the function that you get. So the high-level idea is fairly simple, and actually Hirahara has some results for some related problem as well, which is much tighter than this, but this result is already interesting. And I had independently a similar result for average MCSP with a factor n to the epsilon instead of n to the 1 minus epsilon. So that's for one direction. So it seems at least that MCSP, working with MCSP helps us in terms of hardness amplification. And then we can ask question 2, well, do we get some sort of cryptographic leverage out of the average case hardness of MCSP in this sense?
When you think about the 0 error heuristic for MCSP, that's for what value of SON?
So yeah, you think about it for S being like 2 to the epsilon n, right? I mean, you could also think about it for S being polynomial in n, but then, then you know that you can do it in quasi-polynomial time, so you need to adjust your hardness assumption appropriately. But if, the sort of the standard setting we'll consider is where S is very large, right? It's 2 to the delta n for some delta close to 1, or maybe delta for some other constant delta between 0 and 1. That's a regime where we're typically interested in this question. Okay, so well, I mean, so as I just told you, I mean, natural proofs essentially equivalent to the average case easiness of MCSP in the sense we've defined. So if one-way functions exist, then MCSP is hard on average, right? So if one-way functions exist, so we showed by picture that if exponentially hard one-way functions exist, then MCSP of n to the c is 0 error hard on average for some c. But just by tuning parameters, if one-way functions exist in the standard sort of definition, then you just get the 2 to the epsilon n here. It's just the low end versus the high end in terms of parameters. So for exponential size circuits, you get that MCSP is 0 error hard on average. And what we're interested in doing is exploring whether the second implication can be reversed, right? So whether you can actually get one-way functions from this assumption that MCSP 2 to the epsilon n is 0 error hard on average or not.
But it seems that one-way functions are overkill, right? I mean, it seems that hardness of learning will already imply this kind of things, and we know that hardness of learning can be based on, like, seems to be weaker than one-way functions.
Well, yeah, I mean, so it matters which version of learning you consider. So it's learning with uniform distribution. So yeah, so these things seem to matter here. Yes, yeah, it's sensitive to the distribution over which you're learning. Yeah, and what's the motivation for this? Well, I think it'd be interesting to have an example of a natural computational problem whose average case hardness is equivalent to the existence of one-way functions. I mean, so for example, with NP, I mean, the fact that SAT is NP complete has obviously been hugely influential. I'm not saying that this is sort of completely analogous, but yeah, to have a natural problem that captures one-way functions would be very interesting, I think.
So SDK hardness, for example, implies that this thing is hard, or not?
So it's known that it's known that SDK reduces to MCSP. So MCSP is hard for SDK under probabilistic reductions. So yeah, this is something that's known. Yeah. So yeah, MCSP is hard for SDK, and the question is, well, I mean,
What sizes you get from the reduction? Do you know? Like
for
SDK?
yeah, I mean, so again, I think it's exponential. Yeah, it's exponential, yeah. Yeah.
So if you succeeded in this, will it actually mean that MCSP is potentially lower, right? Because it would give you one-way functions, and we don't know how to do it from Hardness in B.
Yes, but I mean, it could be that MCSP is NP hard, and so yeah, I mean, it's very possible that Pessi-learned and heuristica both vanish, right? Yeah, then neither of them is a valid world, and yeah, we know then there's no relativized way of doing this, but yeah, but it's still a possibility.
Would it necessarily be a non-black box reduction?
Yes, I think so. Yeah. But there's also a relativization barrier, right? I mean, there's relativized worlds where, for each of these worlds, there's a relativized world where it exists. Yeah. So, okay. Okay. So here's the plan for the remainder of the talk. So I'll tell you what I managed to do so far, and yeah. So I mean, I haven't quite managed to solve this, but made some progress. So how much time do I have?
Question. I mean, you know, I guess quantifiers matter and stuff, but if you just define one-way function like it picks a random circuit of size S and outputs its true stable and S, I mean, what goes wrong? The parameters. I mean,
Yeah.
That
doesn't seem to be a good distribution on circuit. I mean, so that's one of the issues somehow, right? Yeah. So I mean. Yeah. So is there a natural distribution on circuits which gives you kind of maybe uniform distribution on easy functions or something close to it? I mean, yeah. There's no.
What about permanence of the random matrix, so like a cleaner model where it's clear what the uniform distribution is?
Permanence of random matrices. So you're thinking of like a higher class or sort of.
A small matrix.
And also, by the way, I think that there are candidate distribution of those circuits. Like you can take, I don't know, there's a circuit, and in each level you do you apply a computation of like a 3 random bits in the circuit, and people believe this is hard, and they can even prove that it's k-wise independent.
Oh yes, yeah, yeah.
No, public. It's a public game.
So isn't that for formulas though? Is it for circuits? It's for circuits. Okay.
No, if it's a permutation, it's public and it's independent.
Yeah. How much? Okay. Thanks. Okay. So yeah. So this is the plan. So first, I'm going to talk about there's actually an equivalence between average case hardness and succinct hitting set generators in a cryptographic setting. And I'll define what these objects are. I don't think they've been studied before, and they might be interesting. And then I'll sort of show that the average case hardness of MCSP implies actually pseudorandom distributions that are supported on succinct strings, on strings of low circuit complexity. And under a certain conjecture about universal constructions of such distributions, we get what we want. But yeah, I mean, you could. So the conjecture, yeah, I don't have a clear path to proving it. It's just something that I pose, and welcome any feedback on it. Okay, so first the equivalence between average case hardness and hitting sets. So yeah, so hitting set generators, yeah, sort of in the complexity theoretic setting, we're interested in them because they help to de-randomize RP, randomized polynomial time with one-sided error, because essentially if you have like a set of random strings, you know that many of them give you a yes answer. You just want one of them that certifies that the answer is yes. So that gives you a hitting set. But so that's what a hitting set generator is. It's an efficiently computable function whose range intersects every dense easy set, right? So you don't want to approximate every dense easy set, but you don't want to approximate every easy set, but you just want to intersect it. And this is widely studied in the complexity theoretic setting, where the generator has more power than the adversary. This is a setting that's useful for de-randomization. So when the generator can run an exponential time, the seed length, and the adversary is, say, some fixed polynomial time, then there's a, oh, sorry? Yes, exactly, yeah. And in this setting where the generator has more power or has kind of exponential power on the seed length, hitting set generators are actually equivalent to pseudorandom generators because hitting set generators imply hard functions in linear exponential time, and then from hard functions in linear exponential time, you can get pseudorandomness. So that's a proof of equivalence. But as far as I know, and I asked quite a few people, perhaps a hitting set for people who know about hitting sets, but none of them knew whether this has been considered before in the crypto literature. So it's not something that has crypto applications, perhaps, but I think it's interesting in this context as a conceptual tool. What's a hitting set generator? A hitting set generator with seed length k is a polynomial time computal function from k of n bits to n bits, such for all large enough n, the range hits every dense set. A 1 over poly n dense set means a set that such that at least 1 over poly n fraction of inputs is in the set, right? So the standard definition of density. And the set is in polynomial size. But here you have something that's computable fixed polynomial size, and it hits every set computable in arbitrary polynomial size. So we're in the crypto setting.
The success probability depends on the size of the set?
You just want...
The hitting probability is fixed?
Yeah, no, there's no probability. It just hits. It just intersects.
No, but the density is
The density. Yeah, the density is fixed. Yeah.
So it doesn't change.
No.
It
Yeah.
might be useful in the applications of the organization of proof. This might give the more efficient versions of the non-interactive commitment, because we want to read sets more efficiently than say missing weaknesses.
Oh, I see.
But there are some functions to concrete fixed polynomial time adversary, like why would we do
To be more efficient.
Yeah, so I guess that may be one possibility. I mean, efficiency might be one reason to care about it. Well, the thing is that it's completely unclear whether this implies PRGs in the crypto setting, and imagine that
Do you think that something like this implies one-way functions?
I don't know. I don't have any sort of strong belief about it. So yeah, if it implied PRGs, it would imply one-way functions, but I don't have any strong belief about it. So this is what a hitting set generator is. And well, what we're interested in is actually a special kind of hitting set generator, a succinct hitting set generator, where the range of the hitting set generator consists of strings of low circuit complexity, right? So just say that a string is S succinct so think of the string y as having length 2 to little n, of having length exponential in little n. And then you can interpret it as the truth table of a Boolean function on n bits, on little n bits, right? And then you can ask if this function that the string y represents has circuit complexity at most s, right? So that's what it means for a string to be S succinct. That means you can compress it using circuits. There's a circuit that kind of, whose truth table is the string y, right? There's a string, circuit of size S whose truth table is a string y. That's what a succinct string is. And an S succinct HSG is just a HSG such that each string in the range is succinct, right? So now you don't really care about the seed length of the HSG so much. You just care that the range has succinct strings in it. And well, one sort of crucial observation here is that there's a universal succinct HSG. Namely, there's like a hitting set generator which works if and only, which is a hitting set generator if there is any hitting set generator, right? There's a universal one. And namely, that's the one that maps a circuit of size S to the corresponding truth table. So this is again something that, that might not be completely clear, but maybe kind of like arguing by picture will make this clearer. And the proposition.
Just because any succinct is a generator is a subset of the universal one.
Yes, exactly. Yeah,
so the succinct one hits the universal one must take it.
Yes, exactly. Yeah. So it's quite easy to see if you kind of picture things right, but maybe I'll just. So the proposition is that hardness on average and zero error is equivalent to the existence of succinct HSGs. And that just actually follows from this picture I had earlier about, here you have like the easy functions, right? So you had the functions that had circuits of size at most S. And if you had a dense easy set here, if MCSP was easy on average, then the hitting set generator, the range needs to live in here, so it can't hit the set, right? So if MCSP was easy on average, there wouldn't be a hitting set generator. And if MCSP was hard on average, then every dense set would intersect this set of easy functions. And so if you just take this entire set, which is itself the range of this universal hitting set generator, which maps circuits of size S to the truth table of that circuit, then that's going to hit the set, right? So by looking at this picture, it's fairly simple to see. But in fact, this is a fairly generic phenomenon. So this notion of succinct hitting set generators is also something that occurs in arithmetic complexity. So in arithmetic complexity, like Boolean complexity, there's barriers proving low bounds, and there's been sort of a proposal for arithmetic natural proofs, for natural proofs barrier there. But we don't have a good candidate, a good example of a hard function of something that corresponds to one-way functions in the Boolean setting, in that setting. And there, what you really need is like an S succinct hitting set generator of a certain form, right? So This kind of connection between succinct hitting set generators and natural proofs is, carries over also to the algebraic setting, which might be interesting. Okay, so that's the first equivalence. So the second sort of implication is, okay, so this is kind of like going a little way. I mean, getting some kinds of hitting site generators, but it's fairly easy to see. And can we get something about pseudo-randomness? And that's what we'll do in this next part. So so an ensemble of distributions Dn or n-bit strings is just pseudo-random if, I'm not going to mention the distinction probability here because it's not very important for this part of the talk, but if this distribution can't be distinguished from uniform by Pauli event size circuits, that's what a pseudo-random distribution is. And we again have this notion of succinctness for pseudo-random distributions, that the distribution is supported on strings that are succinct. And the key thing is that we don't really have any sampleability condition on the ensemble, just that the strings and the support are succinct. And then you can show that if MCSP is hard on average, then there's an S-succinct pseudo-random distribution ensemble, which means that there's a set of pseudo-random distribution which is completely supported on the yes instances of MCSP, right? So MCSP is 0 error hard on average, then you get a pseudo-random distribution that's completely supported on the yes instances of MCSP. And that's stronger than what we had earlier because pseudo-random distributions imply hitting sets. The support of a pseudo-random distribution is a hitting set, but it's unclear whether you can go in the opposite direction, right? So if we could also show that this distribution is sampleable, then we'd be done. We get one-way functions from this.
But it's not like counting argument, because if you don't, you no restriction in the sampling time,
it's not clear because of the succinctness requirement. Yeah. Yeah, it's not clear, but yeah, we could. So yeah, I mean, what's the idea of the proof? I mean, so yeah, it works via this sort of approximate min-max kind of theorems. I mean, something that I think Ronen referred to in his talk as well, where so you define sort of a zero-sum game where somehow one player corresponds to yes instances of the small circuits, and the other player corresponds to polynomial size circuits. And we can use the approximate min-max theorem, we can apply it to this game and show the following, that if the row player has a winning strategy, then there's a succinct pseudo-random distribution ensemble. And the trickier part is to show that if the distinguisher has a winning strategy, then MCSP is easier on average.
Well, as we see in the proof, this conclusion is that it's easy on average uniformly easy or non-uniformly easy?
It's easy on average zero for circuits. For circuits, yes, for circuits, yes, yeah. Oh, so unfortunately, we're not going to see in the proof because that's all. Yeah, it's just going to be a sketch of the proof. But yeah, we could discuss it later.
So what you would need to get this pseudo-random ensemble is that MCSP is hard on average, but it's even hard for circuits on average.
Well, I mean, we're assuming, so when we say hard on average or easy on average, we mean with respect to circuits, right? So our definition is itself with respect to circuits. So easiness on average means that there is a sequence of polynomial size circuits which zero error computes its function with significant probability.
That was since the beginning of the talk?
Well, yeah, I mean, it was since I defined easiness on average, right? So there's a sequence of polynomial size circuits such that, yeah. Yeah, throughout we've been dealing with circuits, yeah. Okay, yeah, and well, I mean, another consequence of this sort of proof is that it's sort of fairly general and applies to other situations. In fact, it applies to any problem that sort of supports a certain kind of extractor called semantic extractors. And for such problems, it translates zero error average case hardness to pseudo-random distributions that are supported on Q. So yeah, I mean, I don't have time to say too much more about this. So, I mean, of course, there's a well-known connection between extractors and PRGs due to Luca, but this is a different connection where if you have a certain property from the extractor, then you can carry through this implication from average case hardness to pseudo-random distributions. And our situation corresponds to the Q, which is MCSP of S. But in fact, we can even apply to random KCNFs. So if random KCNFs with linear number of clauses are zero error hard on average, which is essentially the same thing as Feiger's hypothesis, then there's a pseudo-random distribution supported on satisfiable KCNFs. Okay, so finally, yeah, I'm going to mention this sort of conjecture where we actually get an implication. So there's just a conjecture about universality, right? So universality is a phenomenon that you see quite a lot in crypto. There's universal one-way functions, PRGs. And there's universal S-succinct HSGs for almost trivial reasons, as we saw, because you just take the hitting side generator that takes a circuit as its seed and gets a truth table of that circuit. That's universal. But if you had such a universal construction of pseudo-random distributions, then essentially you'd be done. You'd get the complete set of equivalences that you want, right? So if there is a polynomial time computable function such that its range, such that it induces succinct pseudo-random distributions, meaning that when you apply this function to a uniformly chosen seed, then you get a succinct pseudo-random distribution. Then if there's a universal such one, then we'd be done. We get all these equivalences between crypto, learning, and complexity low bounds. And let me just...
Is it just requiring that the distribution will be efficiently computable? Like, what's the difference?
No, I mean, which distribution? So the distribution we got in our previous result was not sampleable, right?
But if you will throw in the notion of universal, then it will be efficiently sampleable.
But not that. I mean, there's some distribution that's, so yeah, we've got to show that there's some distribution that's sampleable, which captures the notion of succinct pseudo-random distributions, right? Because even in the previous case with HSGs, we had to use that there was a universal one in order to get our equivalence there. And yeah, I mean, this question, well, I mean, if you believe in cryptography, there's likely something like this exists, but can we use what we know about universality to argue something like it is unclear, I guess. Yes, but to do it without using, without constructing PRGs, yeah. So it might be, yeah, it might be much easier. I mean, I don't see why it would be as hard. Yeah.
So G needs to work even if these sort of G has to work even if a not sampleable distribution supports it.
Right, exactly. Yeah. You want to somehow exploit the succinctness that your kind of distribution support on succinct strings. Yeah, but it's unclear whether there's a way to do this. But yeah, that's a question. Yeah.
Does the output of G also have to be succinct? Is that necessary?
No. Yeah. Because I mean, as long as it's a pseudo-random generator, you can kind of stretch the seed and apply GGM to it, and then so it's equivalent to having G being succinct essentially. So if you assume this conjecture, then you get like a really nice set of equivalences. I mean, you get that MCSP with different parameters, the complexity is equivalent. If it's average case hardness with some epsilon greater than 0, is average case hard for every epsilon greater than 0, and one-way functions exist, natural pools don't exist. You can't learn polynomial size circuits, so the uniform distribution polynomial time, et cetera, et cetera. So any number of equivalences. So yeah, and the question is, well, I mean, is there an approach to the conjecture? Is there perhaps a weaker conjecture that implies some of these equivalences or weaker forms of these equivalences? But I think it's just intriguing because the assumption is a kind of a zero-error average case hardness assumption. It's an average case hardness assumption for zero-error algorithms, but you're getting from it some sort of pseudo-randomness, and yeah, we're able to leverage it in various ways. Okay, so this is by far from being the only direction in which you can kind of like push this, approach this question that I asked. We might be able to base one-way functions on some other average case hardness notion for MCSP, say two-sided errors, average case hardness, with respect to certain class of sampleable distributions. That's another possibility. And it might be easier to do because it seems that we're really kind of hampering ourselves by considering the uniform distribution, considering the notion of zero-error average case hardness. Maybe we can be a bit more flexible and get stronger implications. Another possibility is sort of using this learning is hard assumption that Benny and others had in their paper. So they showed that there is no black box way of showing that learning is hard based on NP hardness under certain assumptions. But there's a possibility you could use the learning is hard assumption to get one-way functions. So that's a possibility that one could also explore. And I think the point is that somehow MCSP, it seems that there are certain non-black box techniques that become available to us. There are kind of ways of arguing about implications that aren't necessarily reductions. And perhaps this could be useful in addressing some of these questions. And in general, I mean, I guess it would be nice to see more connections between all of these fields because I think MCSP is very naturally connected to all of these areas, computational learning theory, to cryptography, and I haven't talked about it at all, but also to proof complexity. There's significant connections to proof complexity, going back to the Rosberg-Ulrich work, but there's been more recent work as well. So yeah, and it's interesting because earlier in this workshop, I mean, we heard Alon's talk where in TFNP also there's a similar phenomenon where there's strong connections between the complexity questions there, between cryptography and proof complexity, and here's another space in which similar connections exist. And it would be good to explore them further. That's it. Thanks. Not really. So that's another interesting question. Yeah, to kind of design better than brute force algorithms for MCSP, because so there's this low bound I mentioned for ACC0 of Ryan Williams. It goes via non-trivial algorithms for satisfiability. So he showed that the non-trivial algorithms for C satisfiability, then you get low bounds against C. And it's an open question whether something similar holds for MCSP. If you get non-trivial algorithms for MCSP, do you also get low bounds for corresponding circuit class? So that's another question about MCSP. That's wide open. Yeah.
Could it also be scaled down versions of these functions, like, say, in conjunction way to characterize whether there are pseudo functions in TC0? That you could say.
Pseudo functions where, sorry?
Say you want to ask. So you're trying to characterize whether one-way functions exist. Suppose you want to characterize whether one-way functions in TC0 exist.
Oh, yes, yes.
Then could you do it through the complexity of the minimum TC0 transport?
Yes, all of this goes through, I think. Essentially goes through, yeah. And it's sort of natural because when you have a C where C MCSP is easy on average because C is natural, a class against natural proofs exist, then everything is easy. So you don't have any of these. The various possible equivalents all fail. But when C is, say, TC0, then there's possibility that all of these things are still true. And I think the proofs all work. So, yeah.